Hello everyone. In this video, we're going to talk about two physical quantities called work and kinetic energy. We're going to talk about the work-energy theorem, which gives a relationship between these two quantities. We're going to talk about work and how it can be calculated using the dot product. And then we're going to do a couple of physics examples involving these concepts. Kinetic energy. Kinetic energy refers to the physics quantity that's given by the following formula. If you have an object with a mass of m units and a speed of, let's say, v with no arrow on top of it to indicate that this is speed and not velocity, then the kinetic energy of the object is given by the following formula. The kinetic energy is equal to 1/2 the mass times the speed squared. So as a quick calculation, if you had an object with a mass of 10 kilograms moving at a speed of 50 meters per second, what would the object's kinetic energy be equal to? It would be equal to 1/2 times the mass of 10 times the speed quantity squared. So that would be equal to 5 times, I guess, 2,500, whatever the heck this number is. The exact value doesn't so much matter. For another example, suppose we had an object with a mass of 20 kilograms, but this time we were not told its speed directly. This time we're told its velocity vector. If we wanted to find the object's kinetic energy in this situation, we would have to start by finding the object's speed. And the speed is equal to the magnitude of the velocity vector. So if I use the formula that tells me the magnitude of a vector, I find that the speed corresponding to this velocity is √5 units. Therefore, the kinetic energy would be given by 1/2 times the mass times the speed squared. And as a result, that looks like it'll be equal to 25 units. Now let's put a pause on that and let's talk about another concept called work. Suppose that we have an object that is moving in a straight line path, and let's represent that displacement by a vector, and let's call it lowercase d. Now the whole time it's moving along that displacement, it's being acted upon by a force F that remains constant. So exactly the same force with exactly the same magnitude and exactly the same direction is acting upon this object constantly as it moves. Under that situation, in physics we have a term called work. And the work done by this force acting on this moving object, the work is given by the following expression, the force vector dotted with the displacement vector. The units of work are typically given in joules. Although, I must confess, as a mathematician, units are not the most important thing to me. But let's do a quick example. Suppose we have an object, 1 kilogram, moving from the point 1,3 to the point 2,4. As it moves, it's being acted upon by the force of gravity. So let's find the work done by that gravitational force. So the first thing that I need to do is I need to find vectors representing the force in this problem and representing the displacement in this problem. And for displacement from one point to another, we know that we can find that vector by taking the final position and subtracting the initial position. And if we simplify that, we get the, 3 here, 4 take away 3. We get the displacement vector 1, 1. Now what about the gravitational force here? The gravitational force upon a 1 kilogram object is going to act straight downward, and it's going to have a magnitude of the mass times the acceleration. As a result, I know that the force vector will be equal to 0, negative 9.81 times 3. Since we have an acceleration with a magnitude of negative 9.81 close to Earth, and we have an object with a mass of 3 units. So let's quickly get a decimal approximation here. So now all I need to do to finish this problem, to find the work done, is to calculate the dot product between these two vectors. So multiplying the two x components and the two y components together, I get 0 plus 2.29.43. I get a work done of negative 29.43, I guess I should say joules. Now let's try and figure out what the physics quantity called work is telling us about what's happening with this physical situation here. And to that end, let's explore a couple of examples. First, let's suppose we have an object which is moving in a straight line directly to the right. So the displacement vector is 1 unit in the positive x direction. Now, as it's moving, it's being acted upon by this constant force vector, which is moving down and to the right. Now let's go ahead and calculate the work done by this force on this object, and I can simply take the dot product between the force and the displacement vector, and I get 1 times 1 plus 0 times minus 1, which is equal to positive 1. Now let's think about this situation. If the force vector F here represented the only force acting on this object as it moved, there's no friction, there's no drag, no air resistance, nothing else is happening. If you look at this force vector in green acting upon this moving object in blue, what do you think is going to happen? Is the force vector going to cause the object to speed up, or is it going to cause the object to slow down? I would venture to say that this force is going to cause this object to speed up, because there is overall an alignment between the force vector and the displacement vector. Now let's switch the example slightly. This time our object is still moving directly to the right, but our force vector has a negative x component, and so it's acting down and to the left. Let's find the work done. Once again, taking the dot product between these vectors, I get a value of 1 times negative 1 plus 0 times negative 1. So this time, unlike before our work was positive, now our work is negative. And if I look at how the force is acting on the object as it moves, this time the force and the movement are more or less opposed, and as a result, I would venture to say that this force would cause the object to slow down. So in the case of a positive work, we have a speeding up. In the case of a negative work, we have a slowing down. And that intuition is captured and is made exact in a physics theorem called the work-energy theorem. And it says, if you've got an object with some mass being acted upon by some force, and if you have a sense of the object's kinetic energy before the force was applied, and you have a sense of the object's kinetic energy after the force is applied, what is the relationship between the initial kinetic energy and the final kinetic energy? It's captured by this. The final kinetic energy and the initial kinetic energy, the difference between those two, is exactly equal to the work done by the force on this object as it moves. So this confirms our intuition. if, for example, the work done is positive, then K2 must be larger than KE1. The final kinetic energy is larger than the initial kinetic energy, which means that the object is faster at the end than it was at the beginning. Likewise, if the work is negative, then it must be our initial kinetic energy who is larger. So that means that the initial speed was the higher speed and the object slowed down. Let's put this theorem to work in the following couple of examples. In this example, we have an object with a mass of 5 kilograms, which is moving 2 meters to the right along a frictionless track. And let's suppose the initial speed of this object is 5 meters per second. As it moves, it's acted upon by this force represented by the vector 1, negative 1. So let's try and figure out the object's final speed. So in a situation as complicated as this, I'm going to think about working from the ultimate goal here backward. My goal ultimately is to find the object's final speed. To find its speed at the final time, let's call it v2. Now I do know that v2 is related to the final kinetic energy. I have a formula that says kinetic energy is equal to 1/2 mass times speed. And I know, for example, in this problem that the mass is 5, so I can fill in that blank. So 1/2 times 5, 5/2, v2 squared. Okay, so from this equation, I want v2, and I have a relationship between v2 and the final kinetic energy. If I could figure out the final kinetic energy, then I could figure out v2 just by solving this equation. Now, can I think of a formula that involves Ke2, the final kinetic energy? Well, the work energy theorem says that you can get that using the work energy theorem, calculate the work done, calculate the initial kinetic energy, and then you can solve this equation for Ke2 and get that value. So, tracing my way backward from my ultimate goal, the final speed, I find that if I can just figure out the initial kinetic energy, and if I can figure out the work done, then I will be able to find my way to the final speed. Okay, so first let's find the work done. Now the force vector is given to me directly. The force vector is equal to 1, minus 1. And to get the displacement vector, I'm going to note that the object is being said to move 2 meters directly to the right. So a vector of 2 meters in length, pointing to the right, would be given by 2, 0. The work done would just be the dot product of these two, 2 times 1 plus 0 times minus 1. The work done would be 2 units. Now, looking at this equation here, the next component I need is Ke1, the initial kinetic energy. And I know that this is given by 1/2 times the mass of the object times the initial speed. So let's search the problem. The initial speed is given by 5 meters per second. So plugging that in, I get 125 over 2 joules for the initial kinetic energy. So now that I have the amount of work and I have Ke1, let's go ahead and put that information into the work energy theorem. The work is 2. The initial kinetic energy is 125 over 2. And therefore the final kinetic energy, solving this equation, must be 129 over 2. So now let me go ahead and grab that data and stick it into this equation. If I stick it into that equation, then I know that 129 over 2, the final kinetic energy, must be equal to 5 over 2 times the final speed squared. So if I simplify that, v2 squared must be 129 over 5. And taking the square root of both sides, I find that the final speed is equal to the square root of 129 over 5. So just from the displacement, the initial speed, the mass, and some notion of the forces acting on the object, we can deduce the object's final speed. Pretty cool, I think. For a final example, same setup, except this time the track on which the object is moving does have friction. And we're told that the friction has a magnitude of 0.4 newtons. Let's do the same calculation, but with that added extra complexity. Well, now, in this case, there are two forces acting on this object as it moves, and we need to use the net force to account for both of them. The first force we are given directly. It is this vector represented by this vector 1, -1. Meanwhile, the force of friction also has to be accounted for. Now we're told that the object's movement is to the right. And as a result, the direction in which friction is applied must be to the left, in the opposite direction of movement. So that would be given by a vector with a negative x component and a magnitude of 0.4, so negative 0.4, 0. From that, we can get the net force, the sum of these two, the combined effects of both forces. And if I sum those two together, I get 0.6, -1. Let's call that quantity f with a subscript of n. Why not, for net? Now, if I look at the work done by that net force, by the combination of all those forces acting on this object as it moves, that can be found by using the dot product of our net force with our displacement vector, 2 meters to the right. So that quantity would be equal to 1.2. From that point forward, pretty much every other part of this problem is the same. The work done is slightly smaller now because the force of friction is acting to inhibit the object's movement. But with this now modified work, all the remaining components of this problem would be identical to what it was in the previous example. I would proceed by using the initial speed to find the initial kinetic energy. I would use the work energy theorem to find the final kinetic energy. And then I would use that to find the object's final speed.